Assalamualaikum. We are from BA 2324B and we are going to present about the early stage diabetes risk prediction using Weka. Our group members consist of 5 persons, which is Nur Iman Nazuha, Nur Ayani Sarfina, Nur Shaniza Azwa, Amira Shazmina, and Nur Aisha. For your information, diabetes is a chronic and debilitating disease that affects millions of people worldwide. According to Watson 2023, diabetes mellitus is a metabolic disease that causes high blood sugar. Your body either doesn't make enough insulin or can't effectively use the insulin it makes. Early diagnosis and prevention of diabetes are crucial to prevent complications and improve the quality of life for individuals with diabetes. The early stage diabetes risk prediction dataset was created to facilitate the development of predictive models that can identify individuals at risk of developing diabetes, including demographic information, symptoms, and signs of diabetes, which can be used to train machine learning models to predict the likelihood of diabetes at an early stage. The data set was collected from Sylhet Diabetes Hospital in Bangladesh and approved by a doctor, ensuring the authenticity and validity of the data. The dataset is a valuable resource for researchers, healthcare professionals, and policymakers working on diabetes prevention and management. This dataset can be used to develop predictive models, identify high-risk groups, and develop early warning systems for diabetes risk. This dataset also can be used to evaluate the effectiveness of different interventions and prevention strategies.
Moving on to related works. The first one, dataset composition and pre-processing. A proper pre-processing step, such as handling missing values, normalization, and discretization are crucial in diabetes prediction, emphasize that discretizing continuous variables significantly enhance model performance by making patterns more apparent to algorithms. The second one, attribute significance. Attributes related to symptoms like polyuria and polydipsia often exhibit high predictive power for diabetes. Information gained and chi-square tests to rank attributes, finding that these symptoms were the most predictive. The third one, attribute ranking and feature selection. Feature selection is vital in machine learning research to create simpler, more interpretable models with improved performance. Next, correlation with class variables. Attributes highly correlated with the class variable will generally enhance model robustness. Attributes with moderate correlation can introduce redundancy, requiring careful handling during model development. And the last one, evaluation mode and model validation. Researchers commonly validate their models using separate training and testing datasets to prevent overfitting. Cross-validation were used to ensure the reliability of their diabetes prediction model, a standard practice in evaluating model performance.
For preprocessors, which are divided into classify, associate, and attribute selection. On classify, we have JRIP, 1R, PAT, 0R, and TRISJ48. For associate, we have a priori, while in attribute selection, we have information gain attribute evaluation and correlation attribute evaluation, which will result in output as visualized data. The authors used data mining to analyze the early stage diabetes risk prediction dataset from the UCI machine learning repository. They pre-processed the data, handled missing values, normalized the data, and encoded categorical variables. They then used exploratory data analysis (EDA) to explore the data and identify predictors for diabetes risk. They use classification algorithms like decision trees, GRIP, 1R, PAT, 0R, and TRISJ48 to predict diabetes risk. They also use association rule mining and InfoGain attribute level for attribute selection.
Data preparation phase. The dataset initially contained 17 attribute types, but only 6 key attributes were selected and analyzed further. This filtering process was done to focus the analysis on the most relevant variables, removing any irrelevant or redundant information. The goal was to optimize the effectiveness and accuracy of the subsequent modeling and prediction tasks by working with a streamlined, clean dataset. For the data processing phase, the work from home versus work from office prediction index data contain both numeric and nominal categorical values. To predict the majority class, the researchers employed the 0R classifier, which is the simplest classification method. 0R relies solely on the target variable and ignores all the predictor variables. This analysis aims to understand the influence and relationships between these different attributes. The figure 2 shows the actual original dataset that was used in the analysis. This is the full, unfiltered dataset containing all 17 attribute types that were initially present. In contrast, figure 3 shows the filtered dataset. From the original 17 attributes, only the 6 key attributes were selected and analyzed further. The filtering process removed the unnecessary attributes, leaving just 6 important ones for the final analysis. The purpose of this filtering and data preparation step is to focus the analysis on the most relevant variables, removing any irrelevant or redundant information that could potentially introduce noise or skew the results. By working with the filtered, streamlined dataset shown in Figure 3, the researchers were able to optimize the effectiveness and accuracy of the subsequent modeling and prediction tasks. So, in summary, Figure 2 depicts the raw, unprocessed dataset, while Figure 3 shows the clean, filtered dataset that was used as the input for the main data analysis and modeling phases.
Today, I will present about the data understanding. We have used data mining method to gain the results. This data have 520 instances and 17 attributes. This shows that Weka tool that was applied in this research to analyze the dataset are a practical and effective classification tool. Next, as you can see here in the table, we have the 17 attributes, which are age, gender, polyuria, polydipsia, sudden weight loss, weakness, polyphagia, genital thrush, visual blurring, itching, irritability, delay healing, parietal paresis, muscle stiffness, alopecia, obesity, and class. For the description, it is to describe the attributes that I had said before. And lastly, data type and value. All the data type are the same, which is all attributes data type is nominal. Overall, it can be seen that early stage diabetes risk is classified as low, which is in blue color, followed by the highest, which is red color.
For feature selection using a priori model ranker, this is the attribute selection using feature selection methods, which is infogain attribute evaluation. While this is attribute selection using feature selection methods, correlation attribute evaluations. Using Weka, the feature selection discovers the most influential attribute using infogain's attribute evaluations and correlation-based attribute evaluation shown the most influential attribute contributing class is polyuria attribute number 3. In the early stage diabetes risk prediction data set, the key factors identified through information gain and correlation analysis are attribute 3, polyuria, attribute 4, polydipsia, and attribute 2, gender. Polyuria refers to the conditions where the body produces an unusual high amount of urine, which is often an early indicator of diabetes. Meanwhile, polydipsia, on the other hand, is characterized by excessive and abnormal urge to drink fluids constantly, a response significant fluid loss in the body, and both of these symptoms are critical in assessing diabetes because they signal underlying metabolic disturbance associated with the disease. Additionally, gender plays a significant role in predicting diabetes risk as the prevalence and manifestation of diabetes can vary different males and females. Understanding and analyzing these factors are essential for creating accurate predictive model, enabling identifications and interventions for individuals at risk of developing diabetes. This detection is vital for preventing complications and improving long-term health outcomes.
Next, machine learning evaluation. The result of the decision table of the 0R classifier in the Weka Explorer interface indicates that this classifier, which makes the dominant class prediction, has a TP rate and an FPR of 0.6 and 0.5 for the positive class in relation to the precision and recall being equal to 0.6. Next, when the Weka Explorer interface shows the RIP classifier results, the classifier is able to distinguish 194 out of 325 instances with 59% accuracy, while the rate of incorrectly classified instance is 40%. Next one is 1R classification. As for the test accuracy, it classified 429 of 520 as true and misclassified 91 as false. There is no overlapping between the two sets, which makes the kappa statistic equal to 0. Overall, accuracy and random forest classifier were 89%, showing moderate concordance between the predicted and actual classes. The classifier seems to perform quite well with a mean absolute error of 0. Next, the fourth one is part classifier. It correctly classified 429 out of 520 instances. The overall performance has been quite balanced, with having an average May of 0.1 and the root mean squared error of the model was equal to 0.3, suggesting the accuracy of the part classifier in fusing decision trees and rule-based approach to attain optimal classification performance. Lastly, the result of 0R classifier, in which is based on the majority classification, is positive. The overall accuracy of this model is 61%, and the algorithm was right about 320 of the 520 cases. The confusion metric represents the model's actual and predicted value, with 320 samples correctly classified as positive and 200 misclassified, suggesting that the 0R technique has a limited ability for prediction.
This data describe the outcomes of a decision tree analysis performed on a diabetic dataset with the Weka machine learning program. The decision tree was most likely created using the J48 algorithm, which is Weka's implementation of decision tree technique. The dataset contained 522 cases and 70 variables such as age, gender, polyuria, polydipsia, sudden weight loss, weakness, polyphagia, genital thrush, visual blurring, itching, irritability, delay, healing, partial paresis, muscle, stiffness, alopecia, obesity, and class. The evaluation mode for the decision tree was selected to evaluate all training data. Based on decision tree analysis described above, the decision tree analysis reveals polyuria, polydipsia, gender, sudden weight loss, partial paresis, polyphagia, and irritability as the most influential dimensions for predicting diabetes. These dimensions represent essential symptoms and demographic characteristics influencing the decision tree algorithm's capacity to identify cases as diabetic or non-diabetic. Their high information gain and correlation score demonstrate their significance in the predictive model.
Let's move into the trend analysis. The figures show the distribution of the positive and negative classes according to the age and gender. Blue for positive and red for negative. For the age group 0 to 52 years old, it can be seen the proportion of females in the positive slightly higher than proportion of males. However, in the negative class, the proportion of male is higher than the proportion of females. For the age group 53 until 60 years old, the trend is reversed compared to the younger age group of 0 to 52 years old. In the older age group, the proportion of male in the positive class is higher than the proportion of females. Additionally, in the negative class, the proportion of males is higher than females. In summary, males seem to have a higher proportion in the negative class, while females are higher in the positive class. The next figure displays a trend analysis between gender, which are male and female, and obesity includes no and yes. It shows that for males, the trend leans more toward negative. Meanwhile, for female, the trend leans more toward positive. Overall, the trend depicted in the figure suggests that females reported lower obesity rates compared to males. More males reported having obesity in comparison to females. Thus, there appears to be a relationship between gender and prevalence of obesity, with obesity being more commonly reported among males. The males based on the positive and negative trend analysis color shown between the two factors. The next figure shows a trend analysis of early stage diabetes risk prediction between different age groups and presence of visual blurring. It analyzed the data between the age group of 0 to 52 years old and 53 to 90 years old, and whether subjects are reported having visual blurring symptoms or not. In the younger age group of 0 to 52 years, it can be seen that subjects who did not report visual blurring symptoms had a lower risk prediction for early stage diabetes compared to those who did report visual blurring. This trend is also seen in the older age group of 53 to 90 years old. When looking at the trends between the age group, the data suggests that the risk prediction increases with both increasing age and the presence of visual blurring symptoms. In both age categories, visual blurring seems to correlate with a higher diabetes risk prediction according to this data. This trend analysis provides insight into key factors like age and symptoms that can help predict early stage diabetes risk. This is the last figure. Based on the information provided in the figure, sudden weight loss and weakness diagram, we can analyze trend to predict early stage diabetes risk between the attributes of sudden weight loss and weakness. The diagram used blue and red to denote positive and negative for these attributes. If an individual report no sudden weight loss and no weakness, they will have a lower predict risk for early stage diabetes. This aligns with health trend as unexpected weight loss and feeling weak can be sign of underlying health issue like diabetes. Conversely, an individual reporting yes to sudden weight loss and yes to weakness will be at higher predict risk. This combination of attributes match symptom of early stage diabetes. Similarly, a yes to weight loss and no to weakness indicate a moderate risk level. A weight loss without weakness is somewhat concerning. The lowest predicted risk will be no weight loss and no weakness. Risk is yes to both attributes. This analysis of the figures trend can help identify those most at risk of early stage diabetes based on the represented attribute of sudden weight loss and weakness.
The first recommendation is to use a decision tree and path predictive models and develop using machine learning techniques for real-world diabetes risk and prediction and clinical decision support systems. This model aids in early detection and intervention and can be integrated into EHR system for automated risk assessments. Key attributes like age, BMI, and family history can be monitored over time, enabling informed preventive measures. Another recommendation are using predictive risk analysis tools like decision trees and path models. Early detection program can be evaluated using randomized controlled trials (RCTs). High-risk group receive intensive screening and education comparing their health outcome to a control group. This method establishes the clinical impact and cost benefit of IT-enabled predictive health approach.
For conclusion, based on the analysis conducted using the early-stage diabetes risk prediction dataset through various machine learning techniques in Weka, several key findings can be concluded. The most influential attribute for predicting diabetes risk were found to be polyuria, polydipsia, gender, sudden weight loss, paresthesia, and polyphagia. Decision tree analysis also identified this attribute as critical for diabetes classification. Trend analysis reveal relationship between various attributes like increasing visual blurring with age, higher obesity rate among males, and sudden weight loss and weakness indicating higher diabetes risk. The various classifier models were able to reasonably predict diabetes risk with decision tree and path performing best. Overall, the study was able to explore patterns in the data to better understanding diabetes risk and develop predictive models.
And the last one is future work. Future work in enhancing diabetes risk prediction models could involve several key areas. Implementing advanced machine learning techniques such as deep learning models could significantly improve prediction performance by capturing more complex patterns in the data. Increasing the dataset size and including additional contextual attributes such as genetic information and lifestyle factors would enhance pattern recognition and model accuracy. Developing user-friendly mobile or web applications based on these models could make diabetes risk assessment tools accessible to the public, aiding to awareness and prevention. Validating the models on independent new data and in clinical settings is essential to ensure their reliability and effectiveness in real-world scenarios. Temporal analysis to study how attributes and risks evolve over time could provide deeper insights into diabetes pathogenesis, while comparing model performance across subgroups based on factors like age and gender may offer customized understanding and improve targeted interventions.